So, it turns out that even though we lose a limb, nerves are still active where they would go and still send thought command. So what about if we could get to the nerves? That'd be easy too. The problem is the nerves are too small, too hard to get to, and too difficult to use. They send too weak of a signal. Turns out the muscles actually amplify the signal to a readable amount, up to about 1 millivolt in strength. So we go to our thoughts, then the thoughts are sent to the nerves, which are amplified by our muscles, which then can be read by surface electrodes. This means we do not have to do any surgery whatsoever to get to the nerves, basically avoiding any kind of infection. This is very important because more and more of our troops are coming back from overseas losing limbs. Now, with these new prosthetic devices, they can live as much of a normal life as possible. Our goal as an entire team was to create an arm with 2 degrees of freedom, all thought controlled. We wanted to do wrist rotation and a hand open and close. The muscles we used to measure our wrist rotation were the bicep and tricep, and you can all try this yourself to feel the muscle movement. And for a hand open and closed, we used the top and bottom of the forearm. Now, to help, just 3 major components we needed were the mechanics, electronics, and software. Now, what did all of these teams do? Our electronics team built the computer and also picked up all the signals from the muscles to send to the computer. Our software basically told the computer how to interpret these signals and basically told the arm what to do in response to them. And the mechanics team built the arm itself. And all of these 3 teams basically performed testing independently and simultaneously, but also met with each other to basically just perform testing and to make sure all our parts were compatible. So let's look at the mechanics. Our goal was to create an arm with the 2 degrees of freedom I told you about, the wrist rotation and hand open and close, and also to be in about size with an average adult male. We used a 3D modeling software called SolidWorks to make a design of our arm, as you can see by this picture right here. After we made this design, we used VEX robotic parts, mainly because they were very compatible with each other and readily available in our club. And as you can see on comparison, this is our SolidWorks picture, and this is the real model itself. Let's look at the actual construction. Our goal for our hand was supposed to be a gripper style, with 2 fingers and a thumb. To power both the wrist rotation and the hand open and close, we used 2 types of motors, right there. To also protect our hardware and our motors, also to simulate limits of an actual human, we used what are called limit switches, that when they are pressed, they will stop all motor movement in that direction. And the approximate cost of this was about $55, all the parts included. So here's a video using SolidWorks. It's pretty cool because you can get a 3D view of your entire assembly. You can also see it explode to see all your parts you used, and you can also see it reassemble for you. Keep in mind, this did take a very long time.
My readers.
And this is it, just reassembling.
Okay, so let's talk about what the electronics team did. The electronics team first started with a PIC computer chip. PIC stands for Programmable Interface Controller. This is the PIC chip right here. Now the PIC has an 80 megahertz clock speed and 128K of memory. It has 64 pins. They're very tiny, as you can see around it. As you can see, the PIC itself is smaller than a quarter. Now, how do we get that on here? Well, this is actually a printed circuit board, which allows us to get all these pins accessed through these holes on here. That way we can plug things into the chip, because these are too small. We actually had this, one of our team members, hand solder this to the board. On this side, you see what's called a breadboard. Now, a breadboard is a really great tool for doing rapid prototypes of testing components together. Why is it so great? Well, the reason it's great is that you don't have to solder anything to it. See how it has these rows, and I think they're, as you can see, they're grouped in sets of 5. Well, the wires mimic what soldering would do, and you can, and as long as it's in the same row with one of the holes on here, which are plugged in right there, as long as it's in the same row, it acts as if it's soldered, and so you can just wire them from one point to another to connect a component to the chip. As you can see, here are various other things we had plugged into the chip and components, but I'll tell you about how they work together on the next slide. Here's a diagram of how all the electronics work together. On this side, you see an electrode pair. That's just one of 4 pairs, so we have 8 electrodes total. Here, 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 and here. As I said, this is just one pair. Each pair gives about a millivolt signal, and it sends it to this electrode amplifier. The electrode amplifier multiplies that times 500 and sends that signal to the computer, so it's about half a volt. Once it gets to the computer, there are various ways of adjusting this signal so that we can get the arm to perform the desired function. And so the computer processes it before it sends it to the motor. Here we have 2 ways of adjusting this signal. Down there there's 2 switches, and that allows us to select one of our 4 channels or 4 sets of electrodes. Also, we have a calibration dial. Mode selection dial, really. That selects what mode we want to calibrate, and we have various sensitivity controls so that we can get the signal desired to send out. But by using the calibration dial, we can use this potentiometer, which is a little slider, to adjust it, and we have a single potentiometer, which allows us to adjust everything for the entire arm. After we adjust everything, we can send it to the final motor output, which is, what's going to actually move the hand. But once we get that hand moving, there's 2 things we can do with that. We've got a row of LEDs, and those LEDs can emit, or they can give off, they're little lights, and they can give off various pieces of information. One of those pieces of information would be that we can see how fast or what the motor signal is through numbers. Another piece of information is if all the lights light up, then we know something went wrong and there was an error. We also have limit switches. As Ian said earlier, the limit switches limit how far it can move in one direction or another, or how far it can open or close, so we can keep it accurate to what a human hand can do. Also, so the way those limit switches work is when it goes that far, it hits them, and then it sends a signal to the computer, which then halts all operations and stops it from moving. Let's talk about what the software team did. Now, the software team used 3 main tools to write the software to run the chip and run the entire arm. The first tool they used is simply the C programming language. The C programming language was invented in the 1970s by Bell Laboratories. The C programming language is great because it allows you to quickly write code that runs efficiently on the chip and takes up very little space. Then we use what's called MP Labs. MP Labs is the programming environment provided by the chip manufacturer, Microchip, that's the name of the company. MP Labs allows us to write in the C programming language code that'll operate the arm, and then it will compile it into another program that we can send to the chip, so the chip will understand what we're telling it to do. Then we used something called an ICD. The ICD is a hardware device that sits between the computer and the chip. It does the actual physical linking of the computer and the chip, but it does much more than that. It lets us send the program to the chip, and it lets us go step by step through every single line of code to make sure that the chip doesn't have any bugs and works the way we want it to. Here's the algorithm we used for the software. Let me tell you to keep in mind that this side and this side are happening simultaneously at the exact same time. The first step for both electrodes, or sets of electrodes really, is to collect data. It does that, it takes 1 sample every millisecond. So once it gets 100 samples, and every 100 samples it gets, it calculates a mean absolute value. That mean absolute value is then multiplied by an input gain. Now what's an input gain like? Well, the input gain allows you, it's kind of like, on a stereo, if you have a left and right balance, and you want to get the values like, balanced together, because one electrode might be giving you a lower signal, and would be going like this, and the other one going like that, and you want to compare those on a scale that, so this one's not always going to be lower, so you can see which one's actually giving you the higher signal. So it's what that input gain is, and it multiplies both sides so we can get them on the same level to see which signal's going to be stronger. A threshold, we subtract that from the value. Now what is a threshold? A threshold is, if your arm's like this, it's actually still using muscles, and those muscles are giving off EMG signals. Those EMG signals can make the arm do things that you wouldn't want it to do, and since they are picked up. So it's what that threshold does, is we can subtract subtract a small value, so we can subtract a small value, which lets us eliminate any of that background noise, so we only get the desired signals. Next, we subtract the bicep from the tricep. When we subtract the two, we find out which signal is actually giving us a stronger signal, since they're both scaled up to similar values. And once we get that value, whether it be positive or negative, then we know how strong it should go in one way or the other, or how far it should open or close. Lastly, we multiply it by the output gain. So what the output gain is, it's like on a stereo, if you have a volume control, this just turns up the volume, I guess you could say, or sends it to the motor, so the motor knows, how fast it should go and in what direction. So I want to play this as a video demonstration of the arm actually working.
Hand open. Hand closed. Palm up. Palm down.
As you can see, the arm is doing exactly what the human is doing
Hand open.
in real time. Here you can see,
Hand open.
that's what we did, is we told the
And
various
close.
commands so we could get the data.
Palm up.
We're going to go to the next slide. We told the person who was operating the arm what they should do, whether that was a palm up, palm down, hand open, or hand closed. It's what that does is, this is the thought command. That's what the person wanted to do. On this side, we had what the arm actually did, so what it executed. Let me remind you that these numbers here are percentages of the entire data we collected. We collected 192 samples total. So 23% of those samples were palm up, what we wanted it to do a palm up, and it did those correctly. On this, on the palm down, you can see that 3% of the time it didn't execute a palm down properly, and 19% of the time it executed a palm up properly, but this is out of the entire data. As you can see, our accuracy rating was 82%, which was very accurate, and we were happy with that. As you can tell, we were...
But why don't you finish? Time is up. Finish.
All right.
Okay.
Why did you not finish? So.
As you can see, our experiment was a success with that 89% accuracy rating. This was great because we had 3 groups of kids, of 2 to 4 kids in each group, and they learned about various fields of engineering that they had little to no experience in before. And all these kids together were able to, so those 8 to 10 kids total, were able to make a working myoelectric arm. There were 2 things we could have done differently or would like to do in the future. One of those would be making a custom printed circuit board that we could solder everything to, and there were other various software algorithms we could have used. Here's our parts list. You can see the board, the prototype board was $30, all the electrical components were $16, and all the mechanical components were $55.65.
I am timing how much you've gone over, so we'll know that. So wrap it up then.
Okay, and I just wanted to recognize a couple people. Those people, we had 3 engineers who worked with us, and they just kind of helped guide us along the way. They were Robert Parks, Elliot Rouse, and Dat Tran. They were from the Rehabilitation Institute of Chicago. We also had one school advisor who runs the robotics club here at the school, Nick Mahalik. And then I want to recognize some of my colleagues. We have Emily Austin and Jesse Foreman. They were heads of 2 of the team. And then other people included Landy Gu, Muda Khan, Aaron Rowe, and Luisa Vasquez. Questions?
And judges, they went over 1.3. 1 minute, 30 seconds, and that was before you started recognizing the acknowledgements we took that. Okay.
Okay.
So went over 1.5 minutes.
You must have done some calibration or gotten some background information to associate the specific electrical outputs from the muscles with the desired physical action.
Yes,
Can you tell me about that?
This is actually a real thing going on, where our 3 engineers who came in to help us, they actually work at the Chicago Rehabilitation Institute, and they're doing this basically every day. So essentially, we got our idea for our project off of them, where they're actually working with people who have lost their arm completely, and actually have to have more degrees of freedom included, so they actually reroute their nerves to the chest and read their chest muscles to now control their arm. So we just did a toned down version of